Welcome! We continue what we started in video 9.1, and in this video we're going to bring complex numbers in a form that is much better suited to do actual calculations with them. So we're going to say goodbye to this vector notation, which was very important to define the complex numbers correctly, and go to the so-called Cartesian form or standard form of complex numbers. This little calculation here helps us. We start with an arbitrary complex number z, which is nothing but a two-dimensional vector with real components a, b. Now, by our definition of addition, this is the same as that. This should be obvious. And now comes the important step. This vector 0b can be written as the product. Here this is the multiplication in the complex numbers that we defined in the last video. This can be written as b0 times the vector 0, 1, which is nothing but the imaginary unit. This is done here. b0 times 0, 1 is by definition nothing but b times 0 minus 0 times 1, which is 0. And here b times 1 plus 0 times 0, which is b. So this proves this step. And now, if you remember, there was this embedding called Yoda, which sends a real number a to the vector a0. So here we have the embedding of the real number a plus the embedding of the real number b multiplied, complex multiplied with the imaginary unit I, which was this vector. Now, of course, this looks much worse than the vector we started with. So from now on, we do the following. We drop the circle around the plus and the times, and we identify here the embedding of the number a with the number a itself. So we understand that if there's a real number a, we can also regard it as a complex number lying on the real axis, corresponding to this arrow here, pointing in the real direction. So we're going to identify this awfully looking term here with this. And this is the so-called Cartesian form of the complex number z, and this is much easier to work with. Okay, so simply identifying these vectors on the real axis with the actual number on the real axis gives you this expression here. And this plus now means plus in the complex numbers, and this little dot means multiplication in the complex numbers, but often we simply leave it out. So after doing this identification, the complex numbers can be written as terms like this: a plus b times I. Very important, a and b are real numbers. For those of you who know already a little bit linear algebra, this fact can be expressed as follows. C, the complex numbers, are a two-dimensional real vector space, and the basis is consisting of two vectors, the vector 1, the complex numbers, which is this vector of length 1, and the vector I, which is the vector of length 1 pointing directly upward. And obviously every vector can be written as a real number times 1 plus a real number times the imaginary unit. If you've never heard of linear algebra, terms like vector space or basis, do not worry, it's not important for this chapter. You should simply realize that complex numbers can be written like this in Cartesian form or standard form. Now, if we assume that the distributive law holds in the complex numbers, I'm going to prove all that a little later, then we can multiply two complex numbers in Cartesian form as follows. We simply use the distributive law, so we multiply here and here and here and here and add all these things up. Then we obtain a times z plus a times d times I plus b IC, which I write as BCI using the commutative law. And finally BI times DI, which again using the commutative law I write as BD times I squared. And now the important observation, of course, is that I squared is nothing but -1. So I can put these two together, they don't have an I, and get AC minus BD, and I can pair up these expressions both with an I and get AD plus BC. And now if you look at that, then it should be clear what Hamilton's motivation was for defining complex multiplication the way he did. You see that? This is that and this is that. So this definition, which at first glance looks insane, is very natural. And it already has built in that I squared is -1, or is supposed to be -1. So this is the reason why Hamilton did the things he did. But for the last time, Hamilton's genius was not to use undefined expressions like that. Okay? He used real vectors with two components, something very, very real and not imagined. And using this definition, we simply find that this vector here multiplied with itself gives -1, 0, so -1 in the complex numbers. Okay, now some important notation. If I have a complex number of the form a plus bi, very, very important, a and b must be real numbers. Otherwise, this representation is not unique. Then you can visualize it like that. You have this arrow, then A is the number on the real axis that tells you how far to the right or to the left you have to move, and B is the number on the imaginary axis that tells you how far up or how far down you have to move to end up here at the endpoint of this arrow. Then the number A is called the real part, for obvious reasons, of the complex number, and the number B is called the imaginary part. Very important, B itself, not B times I. B is the imaginary part, so the imaginary part is a real number, not an imaginary number or a complex number, whatever. And a number that is not 0 is called purely imaginary if it can be written as b times I for an arbitrary real number, not 0b. So if the arrow of this number lies on the imaginary axis. Okay, this shouldn't be hard to understand, but still we look at an example. The real part of this complex number is, of course, 2. The imaginary part of this complex number is, pay attention to the minus sign, -5. And very important, it is not -5 times I. Yeah? The imaginary part is a real number. The real part of the imaginary unit I is 0, and the imaginary part is not I itself, but 1, because I can be written as 0 plus 1 times I. So in this form, with real coefficients a and b, here a is 0 and b is 1. So this concludes this rather short video, and now we're finished with the construction or the definition of the complex numbers. Stay tuned. In the next video you're going to learn how to do arithmetic with complex numbers, how to add, subtract, multiply, and most importantly divide complex numbers. I'll be seeing you soon.